All right, thanks everyone for coming to this special Compass seminar. Today I'm very happy to introduce my good old friend Marcus van Lier-Walqui. Marcus graduated with PhD from Meteorology and Physical Oceanography in 2013 from Rosenstiel, and he has since been a scientist at Columbia University / NASA GISS, GISS. And today he'll talk to us about progress on the next generation of Earth system modeling at NASA GISS. Take it away, Marcus.
Thank you, Milan. Thank you all for being here. I know that there's been a lot of seminars, so just one more, hopefully not too painful. Very few equations. Okay, so just generally I want to acknowledge all of the collaborators that I have on this work. As time goes on, I guess I do less work and more administrative work. So yeah, it should really be highlighted here. And of course the funders, people who give us money to actually do this. So what is GISS? So NASA Goddard Institute for Space Studies, which is maybe a strange name for a climate center, but it started out as mostly space, and just to give some brief history, was established as the New York City office of Goddard Space Flight Center, which is down in Greenbelt, Maryland's theoretical division, whatever that means. In '66, we moved to this iconic location above the Seinfeld restaurant, which is also immortalized in Suzanne Vega's Tom's Diner song, if you know that one. Maybe not. Okay, in '81, James Hansen began as director. I joined in 2013, very important day. And 2014, Gavin Schmidt began as director. I didn't know what there's probably other things I should have put in here that I didn't. And what do we do? Well, one of the things that we do that we're sort of best known for is the GISS temp. So it's basically a temperature record that we publish of global temperatures. And it's one of the temperature records that are used when there are headlines for hottest year on record and so on. And there's been work done to sort of quantify uncertainty in that, so it's pretty nicely put together. And I think it used to be that we'd release ours different time from other centers that do it, but now it's all coordinated. So, and then the other big thing is that we maintain a global Earth system model, or climate model as they used to be called ModelE. So I'll talk a little bit about that now. ModelE, these are slides that I just took from Gavin Schmidt literally today. So it's a CMIP class climate model, boundary layer problems, right? So I'll talk a little bit about what that means, and I'll skip through most of this stuff right now. It's a climate model. And why is it called ModelE? Well, it used to just be called the model, and then it became Model 2, and then Model 2 prime, and then Model 3, and then for some reason it became Model E, and the E doesn't stand for Earth, it stands for the letter E, which comes after D, which comes after C, which I guess number 3 would be. It doesn't really make sense. It's called Model E, the E doesn't mean Earth. And so that's kind of continued through the years until the current version, which is Model E3, and we're sort of in development of Model E4 right now. Okay, I'm going to skip all this stuff. It does things. Things have improved. So this is an image of E2 here with a lot of biases in shortwave that have been fixed in E3. So it's constantly evolving, constantly being improved to be more physical, to have more processes, to have better resolution. Like most models are. Okay, so let's get into the meat of it. Earth system models like ModelE and their projections have errors that are mostly a consequence of sort of things that we have to parameterize, right? The things that happen at resolutions below the grid scale. So those are sort of encapsulated in parameterizations. Of course, one of these things is clouds. And the basic theme of this talk is that observations can improve this, right? So we can try to constrain or improve our models by improving their structure and improving also what the value of the parameters are. So choosing values of coefficients in the equations that control processes like clouds so that it produces a better forecast. Okay, now what uncertainties do we actually want to quantify with observations? So I know a lot of people do weather stuff. So let's say we just have some observations. What does it mean to reduce uncertainty with those observations? Well, one way that you can think about it is I have some observations from a satellite, and I just want to know, for example, how hard is it raining, right? So I can improve my estimation of that. What is the state of the atmosphere at this time? I'm just going to improve that with this new observation. Okay, that's great. That's improving a retrieval, for example. Another context might be for something like numerical weather prediction, right? We're predicting weather on short timescales, a week, something like that. And in those cases, really the main uncertainty is sort of the state of the atmosphere that you're beginning your model forecast from, right? So that's sort of state estimation or data assimilation, right? When we talk about data assimilation, that's usually what we mean. We take observations and we improve that initial condition of our model. Now for Earth system models, when you're looking at sort of more climatological timescales, right? Months, years, decades, centuries, the uncertainties of that initial state don't really matter much. It all kind of washes out in the end. We care, and furthermore, we don't really care about when a storm is going to hit. If it's going to hit on Monday or Tuesday or Wednesday or at 5 p.m. or 6 p.m. We care mostly about what's happening climatologically, right? What tends to happen. So for those things, what really matters is the physics. Right? So the physics that I've put into how my system behaves are going to determine whether I end up with more storms in general, or more severe weather outbreaks, or more cold air outbreaks, or something like that. Also, forcing uncertainty matters, right? The amount of aerosols we put into the atmosphere, the amount of CO2 we put into the atmosphere, all that stuff matters as well. This is sort of a diagram from models that describes this. So at sort of short time scales, this is sort of prediction time scale and what percentage of the error each component comes from. So at the sort of shorter time scales, yeah, that internal variability or the initial condition error is most important. And as you continue to go forward in time, the model uncertainty or that physics uncertainty becomes more and more important. It still matters for a numerical weather prediction, but I think data assimilation has gotten so good that you kind of hammer down a lot of those things, which I think is an interesting point. I'm interested to talk about that more if anyone wants to. Okay, all right, now why do we have to parameterize, right? This is, say, a cloud, and there's lots of complexity of motions there, and even on like a weather model grid scale, you're not necessarily resolving all of the things that are happening. At a climate model grid scale, you're not resolving all the detailed motions, and you're not even resolving the cloud, right? I can't necessarily tell the difference between having one cloud or two clouds in my grid cell, right? If I have just a small handful of numbers describing that. So that's a problem. We have these parameterized clouds. And then in addition, inside of the clouds, we have a bunch of little liquid droplets, right, that have varying sizes. And the distribution of those sizes determine whether it's going to start raining, whether it is raining, whether the rain's going to be hard. Basically, that determines our evolution of our system. So we have only a few numbers that we can use to describe that distribution. And so we have to basically represent it statistically. So maybe we have some canonical statistical distribution, probability distribution that describes how many large particles do we have, how many small particles do we have, and then maybe we just have a couple of numbers that describe this distribution. Or we might have something fancier like a bin microphysics or Lagrangian particle-based physics. Okay, so then the issue is that we sort of have parameterized clouds, parameterized microphysics, and then parameterized microphysics inside parameterized clouds. So this is sort of parameterization squared problem. We have sort of this nested set of parameterizations. Okay, so we want to make that better, and what has been sort of the status quo for model tuning? I recommend looking at these two papers that both came out in 2017, and they kind of have extremely similar titles too, which is curious. But basically they describe how these things were tuned historically, which is basically a combination of expert knowledge and maybe some limited one-at-a-time tuning of parameters by hand, which is limited to a certain extent. So, oh, that's basically what I say there. So until recently, we have not really had a methodology to quantify and constrain parameters robustly, and especially if we have numerous parameters and we're not just concerned with improving one at a time, but we want to see what the joint, what all of the parameters together produce the most realistic simulations. We haven't really had a methodology for that, which isn't strictly true. Like even back to 2004, there were people doing sort of multiple parameter estimation in the context of climate models. But it certainly wasn't really done at global centers. So we were sort of motivated to do this and to try it out. And actually some of this work, I should mention that some of this work in this sort of vein was done here by Mohammed Iskandarani, who did some interesting parameter estimation with polynomial chaos, and that actually served for a lot of inspiration for what we did. And basically what we want to do is we want to estimate the best value of parameters, or what the probability of parameters is over the space of parameters, and get some sense of the uncertainty. So we don't want to necessarily just get the best value, but we also want to say, okay, well, what other values are good? And that sort of fits right into a Bayesian perspective, where we might ask the question of what's the probability of some set of parameters x given some observations y. And there's a formula for that. So there's a likelihood function that you basically compare your simulations to the observations. And then there's also prior. So any prior knowledge you have about the parameters goes in here. And then we usually just ignore this denominator, although it's an interesting quantity in its own right. Okay, this is really expensive. So basically the best way to do this parameter estimation is to do, for nonlinear problems, is to do Markov chain Monte Carlo, where basically you take a value of a parameter, you run your model, and then you take a step. And then at that step, you run your model again, and then you compare the two. And if you get something that's better, then you keep your new sample, and you take another step. If you get something that's worse, you probabilistically accept or reject based on some criterion. And you do this basically 1 million times. So, if your simulation takes a day to run, this would take 1 million days to basically create a probability density. So it's too expensive to do for problems that are as expensive as like a climate model or a high resolution level model. So we kind of stick machine learning into this process. And what we do is we initially sample the parameters with the parameter ensemble, run our model, and then train a model surrogate to basically approximate the sensitivity of certain output metrics to perturbations in the parameters. And then we stick that into our sort of Markov chain Monte Carlo loop. So we still do the same parameter estimation we did before, we just replace our actual model with this model surrogate. And hope that the results that come out are also good for the real model. And we call this a calibrated physics ensemble, or CPE. So if I ever use the word CPE, I basically mean this estimate of the probability in these parameters. Oh, and feel free to interrupt me at any time if you have questions. I'm used to being interrupted. So. Okay, so at this point, maybe it makes sense, given like the state of science in general, to ask, well, why do we do this? Why do we estimate parameters? Why not just directly do machine learning parameterizations or replace our models with machine learning? And I think one thing is that estimating and constraining uncertainty is very important. So that is something that we need to do in order to like more accurately inform, say, risk models, is to have some estimate of uncertainties. This isn't impossible with machine learning, but it is a bit tricky. I would say there aren't too many, maybe saying no plausible, but not too many machine learning candidates for online learning. So in other words, if you want to learn with full global simulations, with global observations, that can be pretty difficult. And especially if you're using something like real observations and not just reanalysis, that can be quite tricky. And that kind of feeds into this question also. Are there enough observations to train machine learning models of processes with fidelity? If you want to do something like clouds, you can't really use like a reanalysis data set to do that necessarily. And then I would say also there's not really any machine learning candidates that can learn both at the global scale and then also at a very detailed high resolution scale, say from like a laboratory experiment. And then no matter what, even if you are developing a machine learning replacement for some part of your climate model or for the whole climate model, I would say that a necessary null test is that it has to be better than taking the model that you used to have and using data to make it better. Right? The null test isn't comparing it to just the standard version of your climate model. It's comparing it to the data-driven version of your climate model, the one that's also had an opportunity to learn from the observations. Okay, so now we can ask questions of what parameters. So some people have done this, done studies where they're basically like, okay, we have lots of parameters, we have too many parameters to deal with, can we narrow down the number of parameters to only the ones that matter, and then just perturb those, and not worry about the rest? So this is sort of a common methodology. And so we wanted to look into this. And so basically what we have here is 45 parameters for our model, for ModelE on the bottom. Various things controlling clouds and microphysics and so on. And then a number of outputs, things that we could compare to satellite climatologies. So there's 36 outputs here, 45 parameters there. And this is just simple linear correlation across basically parameter ranges that the experts told us were reasonable. And some of these seem much more important than others. And if you look at these, what you almost certainly cannot read them, but if you have ever, if you know the sort of dirty secrets of how climate models are tuned, you'll see certain parameters pop up here as very important ones, which are the ones that are often sort of tuning knobs used for climate models.
Entrainment.
Yeah, yeah. There's like, and there's also I think snowfall and DCS. Anyway, yeah. Now the interesting thing is that okay, some look more important, some look less important. If we then apply our observational constraints, so we now narrow down the parameter ranges to what's sort of realistic with our observations, what comes out is completely different. Now we see that in this reduced range of the parameter space, that's sort of the realistic range of the parameters, you get a ton of correlation for almost every single parameter. So this sort of idea that you can a priori determine which parameters are important doesn't really match when you can actually apply data to it. And in that case, it appears that a lot more parameters are important. So our general recommendation is use as many parameters as you can when you're doing your tuning. Okay, what outputs? Now this is something that's kind of disturbing. So what you'd ideally like to do is get some satellite data, ask the satellite people, what's your uncertainty on this? And then use that data with its uncertainties to get to sort of probabilistic constraint. One of the issues, however, is though if you have, say, two different satellite products, this is, I believe, for liquid water path, and you compare them and look at the difference, you get well over 100% difference in different regions of the globe. And perhaps it goes without saying that these uncertainties are well above what the published uncertainties are. So two different satellite products disagree by larger than the published uncertainties. So what use exactly is the published uncertainty? Perhaps it's limited. So what we have to do, and what we do for our case, is we develop a special cost function that basically says if I have two observations and like one number is here and one number is there, and my model predicts anything in between those two numbers, I just treat it like it's hit the target perfectly. So this is just sort of a very ad hoc way of dealing with these satellite biases. Okay, and then we stick that into this this pipeline, and this pipeline is basically the same one that I showed before, where we sample and we generate a model surrogate, and then we plug that into this Markov chain Monte Carlo loop. And the one thing that I want to point out here is that we do something that's a little bit, I don't know if I'd call it fancy, but when we do this the first time, we draw samples, parameter samples that are sort of constrained by the observations. And they actually don't look that good. So we take those values and we add them to this parameter sample to retrain the emulator. And then we do this again. And then we take those outputs and we plug them back in to retrain the emulator. And then we do it a third time. And then that third set is what we use as our parameter posterior. So basically what that means is, I don't have anything to draw with, but that's okay. is that we were training this machine learning emulator with, at first, a very broad set of samples, and then increasingly samples that better approximate what the actual probability we were trying to get at is. So it's sort of a way of optimizing our samples that we found to be very important. Okay, so this went into this paper, and the reason why we call this a calibrated physics ensemble is basically because if you just do a perturb parameter ensemble, you just perturb the parameters, run your model, look at the outputs, you can get a lot of samples that are sort of completely out to lunch, right? So this is top of atmosphere absorbed shortwave, and this is sort of allowable range by observations, is this blue band here. My mouse is not showing up there, so maybe I'll just use this later. So this is sort of what's allowable. And all these things are very unrealistic. So perturbing the parameters produces a lot of unrealistic Earths. So what's the value necessarily in analyzing that or presenting that? Instead, we'd rather look at a sample of parameters that still has parameter diversity, so different parameter values, but produces simulations that are more in line with what we expect. And yeah, so let's see, what do I want to say about this? The end result of this process that we do is that if we draw 100 samples from our probability density function and we run them through the model, basically 30 of them are allowable, are sort of good according to all of our satellite metrics. Which doesn't sound that good until you compare it to the original ensemble, and the original ensemble is 450 parameter selections, where 0% were allowable. So we've gone from 0 to 30, which is pretty good. Okay, we have some ongoing development of this. So one of the things that we quickly realized is that this model surrogate that we've generated with machine learning is uncertain, and we never accounted for that uncertainty. So we've now basically fed in some new methodologies to estimate the uncertainty of that ensemble. So that's, if you want to look, there's a paper that goes into different ways of doing uncertainty quantification for machine learning. And basically what it does is that the neural network predicts its own error distribution. And that error distribution is also a loss function in the neural network training. So in that way, it's sort of predicting its own uncertainty. And it makes a difference. This is basically just compared two histograms with and without that uncertainty estimate, and it looks different. Without is yellow, and with is kind of the blue. I realize this is hard to see. So it makes a quantitative difference in terms of what you get out of this parameter estimation process. Okay, observational uncertainty, so other things we need to worry about. That's obviously an issue. I think there's issues with structural uncertainty. So when you're doing this process, the only thing that you're doing is changing parameter values, right? If you have a faulty structure for how clouds are represented, this is not going to necessarily correct anything about that, besides maybe trying to compensate it with parameter changes, which isn't necessarily ideal. And then also, one of the things that you find is that there are some targets that you cannot even reach by parameter perturbation. So in those cases, if you try to run the Bayesian problem, those become the largest term in your cost function. So the metrics that perform worst become the most important metrics for constraining your model, which is absolutely not what you want, right? The things that you can't get kind of matter less. So there's sort of two ad hoc methodologies. What we do is we just inflate uncertainty for those targets, and other groups will just exclude those targets. So there's sort of different approaches here on what you can do. There's other groups, I won't go over this too much. We use Markov chain Monte Carlo. You might look into literature and see people doing history matching, which is a slightly different approach. I won't talk about that necessarily. And then there's also sort of questions of how do you initially do your sampling? Is there any way to put in other information here? And I'll talk a little bit about that later. So basically, is there any way that we can have a more efficient process than just perturbing a bunch of parameters and throwing them into our full planet? one of the things that we have been thinking about with this parameter estimation process is that now that we can estimate uncertainty and constrain uncertainty in observations, we can ask a slightly different question. So we can now that we're using satellites in this quantitative way to reduce uncertainty, we can say if we had a different satellite, how would that reduce my uncertainty differently? So we can start to do something like observing system simulation experiments, where we ask what's the value of a potential new satellite to constrain uncertainty in our model. Right? And this sort of hinges on this idea that the ability to constrain parameter uncertainty with observations implies the ability to quantify the information that those observations are giving you. So we tested this out in a kind of hokey way. We basically took that same calibrated physics ensemble methodology, and we said, what if we had a better satellite measurement for one of these observables? Right? So, well, the first thing we did was we said, what if we have a worse satellite estimate for one of these observables? So we increased the uncertainty in one of the observations. Interestingly, it had zero difference, which is maybe slightly disturbing. So possibly that means that we weren't using information from the satellite in the first place in any sort of quantitative way. If we reduce uncertainty, by the way, they're sort of hand-selected, some parameters and the probability distributions. So if we gained information, that would be shown by a narrowing of the distribution or a shifting of the distribution. So if we reduce uncertainty in this observable, and this observable is basically boundary layer relative humidity, or boundary layer water vapor, rather. If we reduce uncertainty, we get a noticeable impact. So we get reduced uncertainty in a lot of these parameters. And they're actually the parameters that you'd sort of expect to get more information about from boundary layer water vapor. So things related to entrainment, things related to shallow clouds. So they kind of make sense. And if you look at other parameters, like parameters about ice microphysics, they're basically not affected at all. So this methodology seems to make sense.
You mean like bias? Pinning down bias better in some great big average thing? Or do you mean a bunch of samples and how noisy they are? What do you mean by certain, an observation?
It's just basically the assumption. So we haven't actually perturbed the observation at all. We've just perturbed the assumption of what the uncertainty is in that observation. So it is basically the estimate of...
Just widening or narrowing the error bars?
Yeah.
I see. Not a bias at all, just noise.
Not a bias at all, yeah.
Less noise.
So it is sort of a limitation of this process that, we can look at what that uncertainty, how that would change it. I guess we could explore also bias. We could move the observation around a bit and see how it would affect things, but we haven't done that.
Okay.
So we also did a reduction in uncertainty in temperature measurements, which had negligible impact. So we learned certain things from this that, water vapor in general, we're not getting enough information on it to actually constrain our parameters, that if we reduced uncertainty, it would give a constraint, and that temperature is not apparently as important as water vapor. So the idea here is that we can hopefully provide some guidance to, say, new satellite development as to what targets would actually provide constraint to our model. And yeah, it would require something like a nature run that we would compare against, which we did not really do in this case. This was a very sort of proof of concept, but that's what we would need. Okay, so then this sort of goes into like a pipeline that we want to sort of move towards actually being interesting to more people. So if we just look at like how parameters are constrained with some new observations, obviously that's like interesting to the people who develop parameterizations perhaps, and maybe nobody else. If we then look at observables, how basically uncertainty in certain outputs gets constrained, maybe that's interesting. Maybe more people care about like shortwave cloud radiative effect or total liquid water path, but again, it's probably scientists. What we really want to move to is sort of thinking about how potential observations would constrain climate impacts, right? Things like heat waves or late frosts, or even something like equilibrium climate sensitivity is maybe something. Basically, how much will the Earth warm with a given amount of CO2 release. So that's sort of the idea, is that we move towards this pipeline. And we have like a preprint of a BAMS paper. Actually, it's not a preprint anymore, it's published now. So there's a BAMS paper on this. And if anybody's interested, I can also send a link to that. Okay, so and the bottom line is basically that the value of these model improvements should be judged in terms of what actually matters. So what actually matters to most people isn't necessarily an intrinsic parameter. Okay, and yeah, that has a value. Right, there's a paper that says that there's a $10 trillion value for better information. So feel free to cite that paper next time you're looking for a raise. And yeah, we want to use things like these climatic impact drivers as sort of the targets for what we're constraining the uncertainty in. I don't want to talk about that. We tested this out just with ECS and our just attempt at reducing the uncertainty in this sort of hokey way, and found a quantitative difference in the value of ECS in addition to its uncertainty, which is interesting. ECS, again, is equilibrium climate sensitive. So some interesting results there. And this fits into this NASA pyramid of Earth science to action, where at the bottom there's sort of foundational knowledge, technology missions. So this is like the actual satellites that are going out and measuring things. Earth system models sit kind of here, and then over here are sort of the applications and people. And so we're hoping to sort of bridge this gap with some of this work. This is something, if you're ever writing a NASA proposal, to always make reference to the Earth science to action pyramid. Okay. All right, so one of the things that I mentioned was that there's benefit to sort of these physical models, that they can sort of unify knowledge across scales. And so we've also been doing some work at sort of higher resolutions to dig into that. And basically the question is, how do we do that? How do we bridge across these scales from sort of high resolution large eddy simulations to the global models? The global models might be constrained by satellite observations, which is nice. And then where do we sort of build in an observational constraint to our high resolution models? And then how do we do this little sticky bit in between where we're trying to translate across scales? And what we're targeting right now is precipitation processes. So basically this is a size distribution for a cloud, or a number of size distributions for clouds. And basically the evolution in time as the droplets bump into each other and become larger. And you can see that some of these produce rain a lot faster than others, right? So this is sort of the rain side of the spectrum. Right? Rain starts somewhere around there. Now, the thing here is that every single one of these distributions is actually the same distribution according to a climate or weather model. So in other words, these distributions are all indistinguishable in the parameterizations that most models use. So despite the fact that they, in reality, behave quite differently, like we don't have the degrees of freedom to actually predict this diversity of outcomes. Okay, so what we want to do is we want to improve those processes. We want to use whatever data we have available. So we might have fancy microphysics schemes that are a little bit different than our simple ones. And maybe we have observations as well. And we sort of developed a flexible microphysics scheme to be able to constrain this. So we've kind of thrown out a lot of assumptions about the shape of that size distribution, and we predict moments of that size distribution, and then we try to build in whatever limited physical constraints we can, and then and we can sort of choose whatever prognostic moments are best. And I'll get into that in a little bit. I won't go too much into this equation apart from saying that there's sort of two ways that we can vary complexity. We can change the number of prognostic moments, so the number of variables that we're tracking that describe a cloud. And we can also change the complexity of the equation that describes the rates for evaporation or collision coalescence and so on. And then we use Bayesian inference to get our parameters that fit into this equation. So I'm not going to go into these very simplified tests, and I'll just skip right over to the large eddy simulations. So I think that's more interesting. So this is work being led by my postdoc Kate Loftus. She's doing really great work on this. And basically, can we constrain parameters inside of large eddy simulations? So the idea is quite similar to the climate model. We generate an ensemble of different simulations using different perturbed parameters. And this is from the first time that we did this, so it's actually not as bad as this when you perturb the parameters. But in the first time we ran this, we got some parameters that produced cloud and no precipitation. We found some cases that produced cloud and precipitation falling out of the cloud. And then we had some cases that produced only precipitation with no cloud. So I'm not quite sure how that works, but it's possible apparently with parameter perturbation. And then what we do is we compare this with observations, right? And in this case, we don't use real observations. We use a similar large eddy simulation with a reference bin scheme that has many more degrees of freedom. And we use the exact same framework we did before, basically, for the climate model. And we get distributions of the parameters that control the microphysics for this one microphysics problem. So I won't go into detail on these. Will I go into detail on this? Let's see. We are concerned with sort of quantifying uncertainty. So we want to make sure that our parameter samples actually represent the error in our model. So that's what a lot of these things describe. So basically, this is scale spread, and we're finding reasonably good matchup with mean absolute error, and RMSE is a little bit worse, which is telling us that some of the outliers are kind of making us look bad. But basically, our uncertainty quantification is working. Yeah. And one important point here is that this method of constraining parameters in sort of a free-running simulation gives you quantitatively different values than if you offline try to fit those parameters. Right? So another thing that we could do is we just go into our reference scheme. You can't do this with observations, of course, but we could go into our reference scheme and look at what the value of the rates are that come out of it, and directly tune our equations to match those. But that produces a completely different parameter value than what's optimal when you're actually tuning it online. So I think this is a really important point to bring up, in part because the way a lot of machine learning parameterizations are tuned is sort of in an offline method for the most part. So usually what you do is you take a reference scheme and then you generate a zillion simulations of like an offline reference scheme, and then you do sort of a fitting to that with your machine learning algorithm. And then when you plug it into your full model, maybe it doesn't work as well. And certainly that's what we found in terms of doing it with a physical model with parameter estimation. You really need to do the full free-running simulation in order to get proper constraint for the parameters. Okay. Results that Kate has done with this LES case. So this is aerosol, this is rain rate, this is liquid water path. We get good matchup to the stars, which are the bin scheme. And basically the pink is the prior, so that's the prior ensemble. And then when it's constrained with observations, it's this sort of blue line here.
So, Marcus?
Yep.
I'm really glad you're bringing up this auto-conversion problem. Because
Yeah.
I've never really understood why models have so much trouble with it. And is the idea with that you need to do the full simulation that you can't capture the full evolution if you just do offline parameterization?
I think the reason why we couldn't get our offline matches to match up well is that the most important aspects of autoconversion are right as your initial precipitation is starting to form. And then after that, there's sort of there's nonlinear growth, accretion takes over, and the autoconversion values become less important. So you'll still have autoconversion happening, generating new rain particles, but it's less important than that initial phase. So when you train with all of this data, you sort of don't properly emphasize the importance of those particular sort of those points right as you're starting to create this runaway Bayesian coalescence process.
So you need to know the background. You're not in an offline way.
Yeah.
You're not representing the background.
Yeah. Whereas if you use a free running simulation, if you get that wrong, so much of the simulation is going to be wrong that it's just going to be like hitting your parameter estimation with a hammer. So it knows, the free running simulation knows what's important, right? But the process rates themselves don't speak to that. Is
this problem specific to microphysics, or it applies to everything?
I think it probably applies to everything. I mean, in the end, the bottom line is your whole simulation realistic, right? And if you're just looking at the process rates, which of those process rates are the important ones, or the most important ones? Which of those are for especially if you have a thresholding process that's really like something where I have cloud, all of a sudden I have precipitation formation. For something like that, where you have, suddenly your system generates something else, convection could be another example, right? All of a sudden I have convection, or all of a sudden I have organized convection, or ice formation, glaciation, right? For some of those processes, I would guess that they'd be very similar. It's best to constrain with the full free running simulation. Yeah, I think it's a really, we didn't actually expect that, or we thought we could train well enough offline. Because when you look at some of these, and I'll actually back up to this, when you look at some of the fits that we get offline, it's like, they can be like right on there. They can be exactly on our training data pretty much, and look great. And then when you put it online, it doesn't really work well. And even in some cases, like the traditional, Seifert and Beihang, or Krutenhoff and Kogan can be comparably as good as something that you've trained with just tons of data. Which is kind of shocking. Okay, so let's see. So yeah, this is another one just emphasizing that fact. The yellow lines are what we're trying to reach. The blue lines are what we've tuned online, and then the least square is sort of this offline fit. And you can see it does actually more poorly in many cases than the sort of traditional untuned scheme. So this is all put into Hugh Morrison's P3 scheme. More stuff here. So there is one kind of slightly disturbing issue, which is that there's sort of structural mismatch where our simplified model can't match the target. And one consequence for that is that we get a interesting non-convergence in our parameter space. So different iterations of our methodology will produce different results. And basically the only way to fix this that we found is to add in a fudge factor. So basically a term in the cost function that is the structural uncertainty. So it's an inflation in the cost function to do that, basically. And then you basically increase that until you get convergence in all of your different estimation experiments. Okay, that's something to be thought about more. And this is another plot that basically describes that, but the structural term is actually one of the dots. So the structural term is this pink one. This is the percent of total variance, a histogram of the percent of total variance. So in most cases, the structural error is the dominant error term, which is maybe not ideal, but maybe also speaks to the fact that we need to improve our structures. Okay, and then speaking of that, how do we improve our structures? Is there a better way to do it? There is a better way to do it, maybe. So the traditional approach, right, we have cloud droplets and we have rain droplets, right? We have two categories. Two categories and they each have their own numbers, right? I have my number and mass of cloud and I have my number and mass of rain. And then when I want to grow rain droplets, well, I do that by auto-conversion, right? So that's cloud droplets bumping into each other and becoming rain droplets. I could do that by accretion. So accretion is rain droplets bumping into cloud droplets and becoming larger rain droplets. And then there's self-collection. So self-collection is cloud droplets becoming cloud droplets, raindrop becoming raindrops. I mean, in the end, it's just one process, right? It's just liquid droplets bumping into each other. But it's sort of artificially broken up into these three separate processes in models. An alternative approach is to just say, well, all I have is just liquid droplets. I just have liquid droplets of different sizes. And the only process then is self-collection, right? Just droplets bumping into each other. That's the only thing. So this is what we call a single liquid category. And basically that's what we do. We don't have two categories, we just have a single category. Now, if we had two numbers to describe cloud and two numbers to describe rain, then here, equivalently, we should have four numbers to describe this combined category. And in fact, that's what we have. So we have four moments, number, mass, reflectivity, and the fourth moment. And that's what we use to describe this, which is helpful in the sense that when you only have cloud, now, instead of having two variables describe cloud, you have four variables describe cloud. When you only have rain, instead of having two variables describe rain, you have four variables describe rain. Where you have both cloud and rain, you have the same number of prognostic variables. So you've gotten some benefit, perhaps, if you can figure out how to get it to work, to having the single liquid category. That suddenly I have more prognostic variables, I have more degrees of freedom in certain cases than I did before. And there's some evidence that this has some benefit. So we weren't the first to propose this, but Adele Eigel also tested this out in 2022. Hugh Morrison has a recent paper comparing this sort of a single liquid category methodology in idealized box model simulations. Arthur Hugh, postdoc working with me, has tested this out in 3D LES and shown some better characteristics of rainfall and sedimentation especially. Yeah, and then Carol Lamb also has a paper that's sort of more direct machine learning approach to that. And I'll skip through this. This is basically just what I said. Here are the equations for it, which I'm not going to dwell on either. And it's basically in the exact same framework that Kate Loftus used for her LES simulations that I showed before. And it's the same estimation framework. And okay, plugging it in. So this is the prior. This is determined sort of with direct fitting. This is the offline direct fitting. And here's our target along the bottom. This is the 0th moment. So this is number, basically. This is mass. This is the 4th moment. And this is basically reflectivity. This is domain mean of a large eddy simulation doing stratocumulus. And comparing it to our method doesn't look too great. Then we run it through this estimation framework, and the first iteration looks a lot better. So there's some improvement, and then really it's the second iteration where things are starting to look more physical. So this is still in progress, we're still working on this, but it's nice that we can actually, with a single liquid category, we can produce something like a reasonably sharp cloud boundary.
Marcus, why are you using the 4th moment rather than the 2nd? I think the 2nd would be more intuitive.
Yeah, that's a good. We did some tests on which moments are more informative. The higher order moments have more predictive capability for things like collision coalescence. But it's possible, yeah, that the second moment has more is more useful to have. I don't know if you're thinking of radiative properties or.
Yeah, I'm thinking that then you can compare the set to LiDAR.
Yeah, I think that's a really good point, and it maybe speaks to the fact that we are doing this in this idealized framework where we are concentrated largely on collision coalescence, which isn't necessarily ultimately the best target to have if you are concerned with something like radiation or LiDAR. Yeah, I think that's a really good point. So this is basically showing the same thing. This is time evolution of the system. This was the prior. The orange is our target, the blue is our single liquid category boss. After the first round of CPE, it still looks terrible. After the second round, it suddenly looks quite good. And I could show more plots like that. Basically, it's working reasonably well. It's kind of interesting that it takes 2 rounds to get there. Okay, so maybe we're getting to this sort of conversion. I'm running out of time, so I'll just sort of give a hint as to some of the other things that we're doing. This is work that Kate Loftus is doing with Christopher Williams with radar. These are retrievals of using Doppler radar spectra of rain, and basically they're directly retrieving the size distribution of rain from the Doppler radar. And one of the cool things that you can see with these retrievals is that inside the cloud, as you go down in height, so that's these colors here, you start to grow out these larger size particles. So it's interesting that even just in these retrievals, you can see that collisional growth process. And then below the cloud, you can see sort of all size droplets are decreasing, showing evaporation as the rain is falling down. So this is using AppCape, data from the AppCape field campaign off of the coast of Southern California, San Diego. And yeah, we're just going to continue working on this. Kate's been looking at basically assumptions that most schemes use and what the actual size distributions look like. And it can be quite different. So this is sort of interrogating the assumptions that are made in microphysics schemes and saying how well do they do. And then these things have like actual impacts. So the evolution of rain droplets, depending on what you assume, can be completely different. So if we take the assumptions that happen in most schemes, a lot of these droplets will reach the surface, you'll get a higher precipitation rate. Whereas if we do the retrieved properties, we get a lot more evaporating before they hit the ground. So yeah, precipitation efficiency can be completely off. And yeah, I'll skip past that. But basically, we're trying to close this loop here, and the final piece is in between the large eddy simulations and the global model. There needs to be a glue. So if you try to take parameters from here and stick them into here, it doesn't work very well. So you need to have something in the middle, and for that we use single column models of the global model, and those we can directly compare to large eddy simulations. But they have the exact same physics as the global model. So that's sort of a translation layer, and we're using a library of cases to do comparison between the high resolution studies and the single column model. And yeah, so hopefully I'm going to skip past this stuff because I'm going over time. But yeah, I will just end with conclusions that we sort of demonstrated this capability of doing parameter estimation. We're improving it, and we're trying to kind of do the combination across scales from high resolution comparison to observations, and then also satellites comparing to our global maps.
Thanks so much, Marcus. Any questions for Marcus in the room? Sure.
Very interesting. So you have
Oh, wait, I come with the microphone.
Yeah, you can.
So you have a lot going on with the warm rain here, and that seems very complicated in and of itself. But how about if you extend to frozen hydromedias and all the processes there? Is that tractable?
I mean, I think in some senses, like the single liquid category approach is in some ways analogous to like Hughes' P3 scheme, in that the idea is like, whereas instead of having categories for like ROPL and snow and cloud ice or whatever, you have you instead predict the properties of that as you're going along. So that might be equivalent to, instead of having a category of rain and cloud, you predict sort of the properties of the distribution instead. So I'd say there's some sort of commonality there. Ice is, of course, a lot more complicated and scaled.
Any other questions? Brian?
The elephant in the room, structural uncertainty, I guess. And is that the same as this problem that we none of us have a good intuition for high-dimensional space? But apparently all the volumes in the corners, and it's spiky, people will say, or something. So your Latin hypercube sampling doesn't begin to cover the space of multi-parameter, volume possibilities, but you can't afford to try all the combinations. And is that what structural uncertainty is in a way?
I think that's
how are you dealing with this high dimensionality problem?
In the best way we can, which probably isn't good enough. Yeah, so I would say it is separate from the structural problem, because I think the structural problem is also like, you're using the wrong equation. There's no amount of parameter estimation that you can do that's going to solve that.
I see. There's a problem that there's 37 parameters, and then there's which 37, or how you frame what those are. I see.
Yeah, and then as to the multidimensional sampling problem, that is a huge problem, and I mean that is why we have to do this iterative method. So basically, the initial sampling of the space around where the samples are good is so poor that there needs to be some refinement. And so like we've done it this way, but like if you look at Tapio Schneider's group, they have this calibrate emulate sample where they use like an ensemble Kalman smoother to generate the initial samples in a region of the parameter space that they think is good, and then they use that to train their emulator. So there's sort of different methodologies around to how to do that, but I think, yeah, it's not good enough to just do a single Latin hypercube, I would say, is almost definitely the answer. And yeah, there are a lot of secrets in high dimensions that I think we have no intuition for. And I think there's probably a lot of failure modes in high dimensions that we're not necessarily aware of.
Ron, do we have any questions on Zoom?
No, it doesn't look like that.
Okay,
So why did I bring all this equipment here? Someone needs to ask a question from Zoom.
No, I have a question.
Susan? Oh yeah.
Okay, so this is going to be kind of silly, and it might be like, I don't know, you can gauge it, whatever. Okay, so if you have like the most accurate 2 time steps for all of the parameters that we currently have access to, if you take the later time step, could we create the like most accurate way to get the solution, which was the previous time step?
Okay, so let me think. Yeah, I don't know. I guess one question is like, what is the correlation between like your error at the short time scale and like some of your error at your later time steps? And that I'm not sure about either. In some cases, some of these processes grow super nonlinearly. In general, we have the question of like, how much can we constrain at different simulation lengths? So we use 1-year simulations, but a lot of people think that that's not long enough. E3SM did some simulations where they did the first 5 days of every month and used that as their constraints. So there's some weird things that happen there. So what is the impact of looking at the errors in this one part of the simulation for your parameters? I'm not sure in general, and I'm not sure in terms of your question, like could you somehow stitch together the errors at different timescales and have them tell you something? It's possible, yeah. I think it's unknown territory. Right? We've done one thing, and it was basically the first thing that we thought of that might work, and it worked pretty well. And now the question is, now what? How do we optimize this? We have some ideas, but not all of them.
Well, my initial question was that if you were in the audience, what question would you have?
I think the question that I always have is the question of how can we bridge this sort of parameter estimation approach to NWP, to numerical weather prediction, to sort of every single day in the United States, right, multiple models are run for every hour of the day at pretty high resolution. And then we have radars spinning constantly, right? Like all around the United States getting 3-dimensional data on hydrometeors, on precipitation processes, on ice. So you have like this data which is just there all the time. And it has information about what's wrong about our microphysics. It has information about what's actually happening, about what processes are missing, right? How do we quantitatively bridge that gap? Right? We've done it sort of for the climate problem. We can sort of do it in this LES, but in this middle bit where like weather prediction works, how do we get there? And I think once somebody figures out how to get there, that's just going to be an amazing application of some of these methods because it's so much data. That's a question I always have. I always hope that somebody smart is going to figure out the answer to that one.
Well, you said it, we partly figured it out for LES. Is that continental scale LES the answer?
No, the only reason we figured it out for LES is because we run it with periodic boundary conditions with microphysics that we think is good enough to compare to. But you can't do that for numerical weather prediction because you still have the initial condition uncertainty too. So I think it has to be done with data simulation as well. So then it goes to the other question of like, how do we bridge data simulation and parameter estimation? And I think that hasn't been done because data simulation works so well. It works so well just to do the state estimation that I think less emphasis has been put on fixing the physics. And so now all of the machine learning numerical weather prediction systems come out, and they can do both at the same time. Right? And so that's why they're showing such better improvement over traditional numerical weather prediction systems, is because they have flexibility to not have fixed physical equations. So I think what it shows is like, okay, we've missed something. Like just like I said that a null test to compare against a machine learning climate model is a physical climate model that you've constrained the parameters. I think a null test for machine learning numerical weather prediction is a physical numerical weather prediction with data simulation and parameter estimation.
That would be insane.
That would be fun. I think that would be really cool.
Thank you.
Yep.
All right, let's all thank Marcus again.